All right, hi everyone, and welcome to today's lecture on bases. So before I get into talking about bases, I kind of want to review some things I was talking about last time. So namely, the notion of linear independence and span. So let's go through these. Last time, we looked at a lot of examples of linear independence and how you test for vectors to be linear independent. So by way of review, let's do one more example. Let's look at a specific set of vectors in R4. So say I take the vector 10, -3, 4, 1. The vector v2, 5, 1, 1, 1. And then the vector v3, which I'll take to be 20, and then -1, 6, and 3. And what I want to do is I want to see if these three vectors, all of which lie in R4, are linearly independent. So one way to study this is to kind of take this problem right here and convert it into the problem of a matrix equation. So the equation we're interested in, of course, is C1 times V1 plus C2 times V2 plus C3 times V3. We're setting this equal to 0. And we want to find all solutions, C1, C2, C3, that make this equation equal to 0. Well, this is the same thing as the following matrix equation. 10, -3, 4, 1, 5, 1, 1, 1, 20, -1, 6, and 3. Okay. And this is getting multiplied by C1, C2, C3. And we're setting it equal to 0, 0, 0, 0. Now, in order to solve this matrix equation, A times C equals the 0 vector, what we can do is we can try to apply row operations to the matrix A on the left. By doing that, we can attempt to put A in row-reduced echelon form, which will make it really easy to read off potential solutions to this equation. So let's do this. Say we take this matrix, we go down over here, and we try to go through. So I don't know what's going on here. This is slightly weird and disconcerting, but there we go. So, sorry I was having trouble with copy paste for some reason. It would only copy paste twice, but looks like my control key was stuck. So this matrix, we want to put it in row-reduced echelon form, and we can attempt it by doing a sequence of row operations. The first thing I'll do here is I'm going to swap row 1 with row 4. The reason I'm doing this is that row 4 is particularly simple. It starts with a 1. So I'll get the matrix. 1, 1, 3, -3, 1, -1, 4, 1, 6, 10, 5, 20. Next thing I do is I do a long sequence of operations. I add 3 times row 1 to row 2. I'm also going to set row 2 here, or actually row 3, to be equal to row 3 minus 4 times row 1 And finally, I'm going to set row 4 to be equal to row 4 minus 10 times row 1. So 3 different type 3 row operations. Fortunately, the top row stays the same. And now I figure out what happens to the other row. So here I'll have 0. And then 3 times 1 plus 1, so 4. 3 times 3 plus negative 1, so 8. And then down here I will have 0, and then negative 4 plus 1, so I get negative 3 here. And then negative 4 times 3 plus 6, and so I will get negative 6 here. And then down here I'll get 0. Negative 5. And then negative 10. Now what I'll do is I will set, for the next row operation, I'll set row 2 here to be equal to 1/4 times row 2, so I'm performing a row scaling operation. After doing this, I get 1, 1, 3, 0, 1, 2, 0, 1, 2, and then, I'm only scaling the second row, so here I'll get negative 3, negative 6, and here I'll get negative 5, negative 10. After doing this, I can use my second row to cancel out my remaining rows. So row 3 will be equal to row 3 plus 3 times row 2, and row 4 will be equal to row 4 plus 5 times row 2. And finally, I get the matrix 1, 1, 3, 0, 1, 2, 0, 0, 0, 0, 0, 0. So what I can do now is I can take this, take it over here, and I can finalize the process of putting it in row-reduced echelon form. The only thing I have to do is I have to note that 1 here is free, and I can use it to cancel the 1 here. So I can set row 1 to be equal to row 1 minus row 2. 1, 0, and then negative 1, and then down here, 0, 1, 2, 0, 0, 0, 0, 0. And this is now a matrix in row-reduced echelon form, and so we can apply it to study our original linear system. So, going back over here, or would I do it on a different slide? We now have the linear system. This times C1, C2, C3 is equal to 0, 0, 0, 0, which means, of course, that C1 minus C3 is equal to 0, and C2 plus C3 is also equal to 0. So if we want to find a single particular solution, we could take C3 to be equal to 1. If C3 is equal to 1, that implies that C2 is determined by C3, so it's equal to negative 1. And C1 is also determined by C3, so it's equal to 1. So we get the following set of solutions. Oh, I'm sorry. I didn't write this down exactly correct, so let me fix it. C2 should be equal to 2 times C3. And so this C2 plus 2 times C3 is equal to 0. C1 minus C3 is equal to 0. So if we set C3 is equal to 1, that means C2 is equal to -1, or -2, and C1 is equal to +1. So this gives us the following relation between these vectors. 1 times v1 minus 2 times v2 plus 1 times v3 is equal to 0. And you can see the truth of this relation. Sorry, hold on 1 second. I think I may have made one calculation error here, so I just want to double check and see where I made it. Oh, okay. Sorry. The one calculation error I made was that when I subtracted row 2 from row 1, I should have had a +1 here. And so this changes this, so this becomes positive. And now let's write down our particular solution. Again, we can take C3 to be 1, we can take C2 to be -2. And we can take C1 to be -1. And so this changes this. And now this relation is manifestly 2. Because as you can see, if you add 2 copies of V2 to V1, you would get 20 in the first component, -1 in the second, 6 in the third, and 3 in the fourth. So this is a true relation. Thus, these 3 vectors in R4 are not linearly independent. So that completes our review of linear independence. And it also illustrates a technique that I didn't really get to last time, which is that we can use the row-reduced echelon form in matrices that are not square matrices to test linear independence. Now, let's try to combine the notion of linear independence and span into a very, very single important notion. And I mentioned it at the start of the lecture last time. And this is the notion of a basis. N vectors in a vector space are said to form a basis for the vector space V if and only if the following statements are true. V1 through Vn are linear independent, and V1 through Vn span V. So let's do our first example. Suppose we're in R3, and we look at the following 3 vectors. 1, 0, 0, 0, 1, 0. So we call this E1, we call this E2, and we call this E3. So this is the standard basis. Then, if we multiply E1 by C1, and we add it to C2 times E2, plus C3 times E3, we get the vector C1, C2, C3. And so you can see clearly by choosing C1, C2, C3 appropriately that every vector in R3 can be written as a linear combination of these three vectors. But also, as we verified last time, E1, E2, and E3 are linearly independent. So not only do they span the vector space, but they're linearly independent, which means, according to our new definition, they form a basis for the vector space V. Our next goal is to kind of show that the n here, for a given vector space, the n is uniquely determined by the vector space. And so in order to do this, we kind of have to prove several theoretical results. And when we're done, we'll actually have, finally, a rigorous notion of dimension. So here's the first result we have to prove. So suppose we have a spanning set for a vector space V, V1 through Vn. Then any collection of m vectors where m is greater than n is linearly dependent. So this is our first theorem. So here's the proof. And this proof is fairly insightful. So suppose we have vectors u1 all the way through um. Then what we can do is we can write these m vectors in terms of the spanning set. So we can write u1 is equal to alpha, and I'm going to use a superscript. Actually, no, I won't. I'll use alpha 1, 1 times v1 plus alpha 1, 2 times v2 plus blah, 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 alpha 1 n times vn. And the reason we get this expression is because the v's form a spanning set. So we can write every vector in particular, or every vector in v in terms of v1 through vn. In particular, we can do that for u1. We can do that for u2. In general, we can do it for ui. So we can write this as alpha i1 v1 plus alpha i2 v2 plus blah, 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 alpha I n times Vn. And we can keep doing this all the way until we get down to um. And this will be equal to alpha, this will be alpha m1 times v1 plus alpha m2 times v2 plus blah, 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 alpha mn times vn. So we have a bunch of alpha ij's. And what we're going to do is we're going to study these alpha ij's in terms of a matrix. So actually, before I do that, I want to kind of make some observations. One thing we can do is then we can try to form linear combinations of the u1 through um. So we can try to seek a linear combination c1 times u1 plus c2 times u2 plus blah, 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 cm times um is equal to 0. But forming such a linear combination corresponds to taking all of these and forming a linear combination of these relations, which give us the new relations v1 times the sum from I equals 1 to m of ci times alpha I1 plus the sum from I equals 1 to m of ci times alpha I2 times v2 and then plus blah 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 the sum from I equals 1 to m of c I alpha im vm. So this gives us a linear combination of the vectors v1 through vm in terms of these coefficients, each of which are sums. So let's think of what we've done so far. We started with a combination of the vectors u1 through um, and we had it equal to 0. And then, using the fact that v1 through vn formed a spanning set, we re-expressed this linear combination in terms of a linear combination of the vectors v1 through vn. So I'm sorry, I should have no, I'm sorry. This is correct. The only thing I had incorrect was this should be vn. So let me fix that over here as well. Now everything's good. So by switching from a linear combination of the vectors u1 through um to a linear combination of the vectors v1 through vn, I can interpret this as a matrix system. And so here's the matrix system. If this is all equal to 0, then the matrix system I'm trying to solve is going to be this one. So here I'm going to have the vector with coefficients c1, c2, blah, 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 all the way through cm. And here I will have alpha 1, 1, alpha 2, 1, blah, 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 alpha nm, or I'm sorry, alpha m1, and then alpha 1, 2, alpha 2, 2, blah, 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 alpha m2, and then I go all the way down until I get to alpha 1n, and this will be times, so it's going to multiply by c1, so the next one over is alpha 2n, blah, 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 alpha mn, and so that completes that side of the matrix. And this is getting set equal to 0, 0, 0. So this right here is an n by m matrix. This is a m by 1 vector. And this right here is a n by 1 vector. Now, the advantage of understanding this equation as a matrix equation is that since we know here that M is greater than N, and that this is a homogeneous system, then one of our results that we proved in the first week on linear systems tells us that if we have more variables than we have, if we have more unknowns, then we do kind of, how should I say this? Maybe I'll just show you guys the actual theorem. So we go all the way back to, I believe it was in this chapter. Or maybe it wasn't. Okay, so it's theorem 1.21. So it's up here. Okay. Okay, so maybe the textbook doesn't prove it, but it does say it. If we have a system of m linear equations and n unknowns, then the system is underdetermined. And that is exactly the situation we're in here. And because the system is underdetermined, it guarantees that at least one solution exists, or at least one non-trivial solution exists. So the fact that m is greater than n, and this is a homogeneous system, means that it's underdetermined, which implies that at least one non-trivial solution exists. So even though the book doesn't prove this, let me explain how it is proved. What you do is you apply Gauss-Jordan row reduction to this matrix right here by doing matrix or row operations on the left. And eventually you'll see that the maximum number of kind of free variables you can get is n, but you have more the maximum number of bound variables you can get is n, but you'll always still have a few extra bound or free variables, and those free variables you can set to be whatever you want. And abstractly, that tells you that at least one non-trivial solution has to exist. So, since we have shown that a solution to this exists, it shows that a solution to this exists, which shows that any time we have a spanning set with n vectors, and we have a set of m vectors where m is greater than n, that set has to be linearly dependent. So that completes the proof of our first theorem. The next theorem I want to look at is a consequence of it. So, this theorem is a bit simpler, but it depends on the previous one. So, if both v1 through vn, this set, and the set of vectors u1 through um are bases for a vector space V, then n has to be equal to m. So let's do the proof of this. suppose n is greater than m, then since u1 through um span V, the set v1 through vn must be linearly dependent by the previous theorem. So this is a contradiction because we're also assuming the set v1 through vn is a basis. So this assumption has to be false. So there's no way that n can be bigger than m. Likewise, we cannot assume m is greater than n. Because if we do that, we'll lead to a contradiction in a similar way, because we know that since v1 through vn span the vector space V, if m was greater than n, we'd have to have some sort of linear dependence relation between them. So this shows that we must have n is equal to m. So it's a pretty easy proof, and it follows directly from the preceding theorem. But it does lead us to the following incredibly important definition. And here it is. So let's let V be a vector space. If V has a basis consisting of n vectors, we say that V has dimension n. The subspace 0 of V is said to have dimension 0. V is said to be finite dimensional if there exists a set of vectors that spans V, a finite set of vectors that spans V. Otherwise, we say that V is infinite dimensional. So this is finally our notion of dimension. So let's do an example. Suppose we look at R3. Then R3 can be written as the span of E1, E2, and E3, where these are the standard basis vectors that I wrote down before. And since these three vectors are linearly independent, we have that the dimension of R3 is equal to 3. That's easy. Now let's look at a subset of R3. Namely, let's look at the subset S, which will be the span of 1, 2, 0, and then 1, negative 1, negative 1, and 2, 0, negative 1. And so this is a subset of R3, and the question is, what is the dimension of S? Well, one thing we can observe here is that if we call this vector right here v1, we call this vector right here v2, and we call this vector right here v3, we have, of course, v1 plus v2 plus v3 is equal to minus v3 is equal to 0. Now, this has an implication, namely that these three vectors here are linearly dependent. So, here's my claim. It has two parts, v1 and v2 are linearly independent. And the second part of my claim is that the span of v1, v2, and v3 is in fact equal to the span of v1 and v2. And if you have both of these things, if you know both of these things to be true, then in fact it follows that the dimension of S is going to be equal to 2. So, even though this is a subspace of R3 that's generated by three vectors, you only need two vectors to generate the subspace. And those two vectors turn out to be linearly independent, and they span the whole space, so the dimension of S will be 2. So the real thing that we'd have to do if we wanted to prove that the dimension of S is 2 is we'd have to verify this claim. Now, I could verify it in this specific case, but because I'm going to eventually prove it in general in about 5 minutes, I'll save it for that and leave this as motivation. So let's do a little bit more theory. I want to consider the following theorem. So suppose V is a vector space of dimension n, and we have a set of V is a vector space of dimension n, then any set of n linearly independent vectors spans V, and any n vectors that span V are linearly independent. So let's prove this. And this will give us as a special case this statement. So I'm going to divide the proof of this into two parts. The first thing I'll do is I'll prove part 1, and then I'll prove part 2. Okay? So suppose V1 through Vn are linearly independent. Then what we can do is we can consider the set V1, V through Vn with an extra vector V, where V is an element of our vector space. Then the set V1 through Vn must be linearly dependent. Why does this set have to be linearly dependent? Well, this follows from our preceding theorem. Namely, that if we have any collection of m vectors in V where m is greater than n, the set has to be linearly dependent. So since this set is linearly dependent, we have to have a relation C1 times V1 plus blah, 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 Cn times Vn plus alpha times V is equal to 0 by the preceding theorem. Now what we want to do is we want to study this relation. So here's my claim, and my claim is that alpha cannot be equal to 0. Because if alpha was 0, then we could essentially just get rid of this, and we would have a linear dependence relation between v1 through vn, but that would contradict the fact that v1 through vn are linearly independent. So we must have alpha is not equal to 0. Thus, we can write v as negative c1 divided by alpha times v1 plus negative c2 divided by alpha times v2 plus blah 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 negative Cn divided by alpha times Vn. And this shows that V is an element of the span of the vectors V1 through Vn. So this original set of n vectors actually spans the vector space. And since we know it to be linearly independent, it follows that the set is actually a basis. So that completes the proof of statement 1 here. Now let's look towards a proof of statement 2. So what we need to show is that any set of n vectors that span V are linearly independent. So here's what we can do. We can say, suppose V1 through Vn span V, and V1 through Vn are not linearly independent. Well, what this means is that I can essentially remove one of these vectors from this set, and my set will still span V. So then, after maybe relabeling, we can find a relation that says that C1 times V1 plus blah 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 Cn times Vn is equal to 0, where I may assume that Cn is not equal to 0. So I can write Vn here as negative C1 divided by Cn times V1 plus blah 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 negative Cn minus 1 divided by Cn times V n minus 1. So the importance of this relation is that anytime I have like any vector w that's written as like say alpha 1 times v1 plus blah 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 blah, alpha n minus 1, or actually no, alpha n times vn, what I can do is I can take this and I can substitute it for this vn here. If I do that, I find that w here is going to be equal to alpha 1 plus negative alpha n c1 divided by cn times v1 plus blah 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 alpha n minus 1 plus negative alpha n cn minus 1 divided by cn, all multiplied by v n minus 1. So anything that I can express as a linear combination of v1 through vn, I can actually express as a linear combination of v1 through vn minus 1 by back substituting in this relation. And this shows that the span of v1 through vn is actually equal to the span of v1 through vn minus 1. The key implication here is that I can keep doing this process of basically removing vectors from this list until I eventually reach a list that both spans v and is linearly independent. But if I can do that, then I will produce a list of vectors that has an n small, that has a number smaller than n, that is a basis of v. And that contradicts the theorem that the basis number is uniquely determined. So I won't write all that down here, but the argument basically follows exactly from this key statement. And this completes the proof of this theorem. So I have one more theoretical result to go before I turn to examples, but it's going to follow basically from all the work we've already done. So let's suppose that V is a vector space of dimension n. Then no fewer than n vectors can span V. And any subset of fewer than n linearly independent vectors can be extended to form a basis for V. And finally, any spanning set that contains more than n vectors can be pared down to form a basis for V. So the proof is going to be very easy for us at this point. So I'll start by noting that for 3 here, this is exactly the argument used to prove part 2 of the last theorem. Basically what you do is you just take your spanning set, and anytime you have a linear dependence relation, you can kind of remove that you can use that linear dependence relation to remove an entry from this list and still have a spanning set. So I don't have to prove 3 because I've basically done all the work already. Now for 2, what we do is simply add vectors to the list or to the set that do not lie in the span until the set becomes a spanning set. Now, in order to see why this works, suppose that W is an element of the vector space V, but W is not inside the span of V1 through Vk. Then any relation C1 V1 plus C2 V2 plus blah 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 CK VK plus alpha W set equal to 0 implies C1 through CK and alpha all have to be equal to 0. Because otherwise, I would be able to express, if alpha here wasn't 0, then I would be able to express W in terms of V1 through Vk, which would mean W has to lie inside the span. But by assumption, it does not lie in the span. And if alpha was 0, then that would imply we have a relation between V1 through Vk, but we're assuming V1 through Vk is linearly independent, which means that C1 through Ck has to be 0. So either way, we learn this, which means by adjoining an element that's not inside the span, we get another linearly independent set if V1 through Vk is already linearly independent. So that's all you have to do to prove part 2. And now, finally, let's do part 1. So part 1 follows from part 3 by pairing a given set of vectors down to a linearly independent spanning set. So, all we have to do is we take our arbitrary set of, like suppose that we have like k vectors that span V. Then we can pair this set of k vectors down to a set that's linearly independent that still spans V. And in which case, the size of the set, or the set itself would form a basis for V, but because k would be less than n, we would obtain a contradiction with the fact that the dimension of a vector space is uniquely determined. So I don't want to write all that out in detail, but it is a relatively straightforward argument, and you can check it in the book if you'd like to see how it goes. So this completes all the theoretical work that we need to do to understand bases. And these theorems are going to kind of provide justification for a lot of the arguments going forward. In particular, we can go back to the argument we wanted to make earlier. So here we have three vectors. These three vectors, as we remarked earlier, were not linearly independent, so they could not form a basis. But v1 and v2 are linearly independent, so by removing v3, we get a smaller set, but the smaller set still spans the same space. And thus, we're able to conclude, using our general theorems, that the dimension of S is equal to 2. Okay. So let's do another interesting example. Let's look at Rx. So if you'll recall, Rx is going to be the set of polynomials C0 plus C1 times x plus C2 times x squared plus blah, 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 Cn times x to the n. And so here's our claim. Rx is infinite dimensional. So here's how we'll prove that. Consider the sets Rk, and this is going to be the set of polynomials 1, x squared, all the way up until xn. Then all the way up until x to the k. Then Rk is a linearly independent set. All right. So, what do? We look at this set right here, and we want to show that it's linearly independent. If we show that it's linearly independent for all k, then it will follow that the dimension of this set, this Rx, the set of all polynomials, in fact has to be bigger than k for any k, which would show that the dimension of this has to be infinite dimensional. So here's how we can prove it. We can look at the Wronskian. The Wronskian of 1 x squared all the way through xk is going to be the determinant of the following matrix. So here I'll have 1, here I'll have x, and then I'll have 1 here. Here I'll have x squared, and then I'll have 2x, and then I'll have 2 here. Here I'll have x cubed, 3x squared, 6x to the, or 6x here, and then just 6 here, and then blah, 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 all the way down to k factorial here, and then k factorial times x all the way up over to xk. And so here I'm just using the fact that if f of x is equal to x to the k, or how about I'll just put it more generally, x to the I, then and j is less than or equal to I, then the jth derivative of x is equal to j factorial or not quite. It's equal to I factorial divided by I minus j factorial times x to the I minus j. So I can use this formula to fill out this matrix. And because this matrix right here is an upper triangular matrix, the determinant is just the product of all the things along the diagonal. So this determinant is equal to 1 times 2 times 6 times blah, 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 times k factorial, which, whatever number that is not equal to 0. So because the Wronskian doesn't vanish, it follows by the result we proved last time, and I'll just show it to you guys here, that these k functions have to be linearly independent. And because they're linearly independent, we can now look at the set Rk. And we deduce that the dimension of the set of polynomials has to be greater than or equal to the dimension of the span of 1 through xk. And because 1x all the way through xk are linearly independent, the dimension of the span is just k. And now we've chosen k arbitrarily, so we conclude that this implies that the dimension of the space of polynomials is in fact infinite dimensional. And so that completes the proof. So let's do another calculation. Let's suppose we look at some vectors in R3. And suppose we take the vector -1, 5, 6. This will be my v1. My v2 here will be 1, 0, 1. And my v3 here will be 4, 0, 2. And so the question is, do v1, v2, v3 form a basis for R3? If so, write E1 in terms of them. Where, of course, I'll recall that E1 here is the vector 1, 0, 0. Now, here's what we need to check. We need to check that the vectors v1, v2, and v3 are linearly independent. We know that the dimension of R3 is 3. And it follows from this theorem that, actually, do I use this one or do I use the preceding one? If we can show that all 3 of those vectors are linearly independent, because the dimension of R3 is 3, those 3 vectors have to span R3, which means they have to be a basis. So it suffices to check if v1, v2, and V3 are linearly independent. And so we'll do that. In order to address the question of linear independence, we go about it the same way we've done such problems before, which is that we take these three vectors and we turn them into a matrix. -1, 5, 6, 1, 0, 1, and then 4, 0, 2. And so what we're going to do is we're going to study this by performing a sequence of row operations. So the first thing I'll do is I will set, well, actually maybe I won't do this via a sequence of row operations because there's kind of an easier way to do it. If this is my matrix A, what I want to do is I want to check that this matrix is non-singular. So linear independence of V1, or V1, V2, and V3 is equivalent to the determinant of A not being equal to 0. So I'm going to approach it from this end. I can easily compute the determinant of A by doing a cofactor expansion along the second row. So we can compute det A by cofactor expanding along row 2. And if we do that, then we find that the determinant of A is going to be equal to -1 times the determinant of 1, 4, 1, 2, and then multiplied by 5. And so this will be -1 times -2 times 5, which will all be equal to 10. So since the determinant of this doesn't vanish, this shows that these three vectors are linearly independent. So yes, E1, or V1, V2, and V3 form a basis. The next thing we want to do is we want to kind of see if not only do they form a basis, but if we can express the vector E1 in terms of them. So this means that we're going to consider the following linear system. So we want to look at -1, 5, 6, 1, 0, 1, and then 4, 0, 2. And we want to study the system. C1, C2, C3, getting multiplied by this matrix is equal to the vector 1, 0, 0. So one way we can do this is we can essentially attempt to perform row operations on this matrix to put it into row-reduced echelon form. And if we do that, that essentially corresponds to when we do the when we multiply this matrix through by the elementary matrices, it'll result in solving for C1, C2, C3. So we did this kind of calculation the first week of class, and so we'll do it again right now. What we do is we take this linear system and we regard it as an augmented matrix. So negative 1, 1, 4, and we'll put our little augment bar here. 5, 0, 0, 6, 1, 2. And now we apply row operations to this augmented matrix, and we attempt to reduce the left side of the augmented matrix to the identity. So the first thing we'll do is we will set row 2 to be equal to row 2 plus 5 row 1. And we'll set row 3 here to be equal to row 3 plus 6 row 1. If we do that, we're going to have negative 1, 1, 4, 1, 0. And then here we'll have 5, and here we'll have 6. This will cancel, this will cancel. I'll have 5 here, 20 here. And then I'll have 7 here. 7 times 4 is 28. 28 plus 2 is 30. So I have this. And now I will write, or I'm going to scale row 2 by 5. So I'll set row 2 to be equal to 1/5 row 2. And so I have negative 1, 1, 4 for the first row, 0, 1, 4, 1 for the second row, 0, 7, 36 for the third row. And now I will set row 3 to be equal to row 3 minus 7 times row 2. If I do that, then I will have negative 1, 1, 4, 0, 1, 4, 0, 0, and then 2. On the other side, I'll have 1, 1, and now I'm subtracting 7 times 1 from 6, so I'll have negative 1 here. And I now have this matrix, which is now an upper triangular form. And so I want to finish putting it in row-reduced echelon form. So what I can do is I can set row 2 to be equal to row 2 minus 2 times row 3. I can set row 1 to be equal to row 1 minus 2 times row 1. And I'll have negative 1, 1, 1, 0, 0, 0, 2, 0, 0. And I'll have negative 1 here. And whereas, let's see, okay, that was a 1. I was just double checking. So here I will now have 3 and 3, which means I can set row 1 to be equal to row 2 minus row 1. Or I'm sorry, we can set row 1 to be equal to row 1 minus row 2. If we do that, we're going to get negative 1, 0, 0, 0, 0, 1, 0, 0, 0, 2. And then here I'll have 3, and here I'll have negative 1. Okay, now I could keep trying to put the left side into the identity form, but I don't really need to. I'm basically done because this tells us that C1 here is equal to 0. It tells us that C2 is equal to 3. And it tells us that C3 is equal to negative 1/2.